Okay, this is the demonstration video for project 2. So we're going to start out by creating a new project in Xilinx, and we'll call it project 2. I want to make sure that our top level source type is HDL. No, I apparently already made one like this, so I'm going to overwrite it. So we'll click next, finish. Then we're going to go ahead and head over to project, add a new source. We want this to be a Verilog module. I'm going to also call this one project 2. Go next. We'll fill in all this input stuff later and finish. And here we have our empty module. So we're going to start out with declaring our inputs and outputs. So the project said we had to have two 4-bit inputs, so I'm just going to call those A and B. And we're going to have to add those together, so the result of any addition is going to be a sum, so that'll be one of our outputs. We also have to account for overflow, so that will be an output as well. And this all has to go to a 7-segment display, so we'll just call that one display. Oops, display. So now we go ahead and start to say what our inputs or outputs are and their sizes. So we'll start with A, so that's an input, and we use the square brackets to denote a bus, so that's basically anything over 1 bit. You'll want to say how large it is. So that's A, and input 30B. And for our overflow, that's only 1 bit, and since we want to be able to actually look at it in the timing diagram, we're going to want to call it an output register. So we'll go output reg overflow. Now for our sum, that one is going to be also 4 bits. And we want to be able to look at that as well. So that would have a similar syntax to our inputs, except we're saying output register sum. And we are also outputting to our display, and we want to be able to see that on the diagram, so that's an output register. Now a 7-segment display is a 7-bit display, so we would want to say 6, 0 display. Alright, now on to the fun part. So we're going to start our adder right here with a always at. Now the conditions that we want to check for in this is whenever there's a change to A or B, because that's really the only two things that we're adding here are A and B. So we'll go ahead and start that up. Now when we do our addition, we want to be able to account for this overflow. So we're going to use something called concatenation. So what that is if the result of sum is larger than the size of the sum, so basically if it's larger than 4 bits, then we are going to concatenate or append a 1 onto the end of it, which is going to be our overflow here. So you'll want to say overflow, and this is inside of a curly bracket, by the way. our overflow, and our sum, and that equals A plus B. So pretty simple. Luckily, the addition in Verilog is extremely easy. So we'll end our adder right here by saying end. Alright, so now that is taken care of. So now we're going to go ahead and begin our 7 segments display. Now, before I go and do all this, I just want to let you all know that there are multiple ways to do at least this part. I mean, there are multiple ways to do the addition, but I've found that the concatenation is the easiest way and the most efficient way to accomplish this. Now, I went ahead and used a bunch of case statements for my 7-segment display. I know that some of you did a series of if statements, which is fine. Basically, as long as you get the correct outputs, whichever way you get there is negligible. I mean, some ways are a bit more efficient than others, but as long as you arrive at the correct answer, that's essentially what we're looking for. So we'll start with our always block. Now, what we're going to want to check for is whenever sum changes. So we're going to put that in there and begin. Now, I did case statements, so I would say case, and I'm checking for sum. Oops. Oh my god, I cannot type today. Checking for sum in those cases. Now, what we're doing here is we say our outputs. So if our sum is 0, so that would be 4 comma b 0 0 0 0, and we put a colon in here, and then we'll say display y equals 7 comma b 2 4 5 6 7. Now this equals 0 on a 7-segment display. So if you go ahead and take a look, perhaps elsewhere, at a 7-segment display, you will notice that, here I'll do a brief little, oops. So this is A, B, C, D, E, F, and G, each one of these numbers. So these ones here, these mean that that segment of the display is illuminated, and the 0 means it's off. So if you look at a 7-segment display and see how the segments are aligned, then you can see that all of these ones correspond to the number 0 being lit up, and this one is that little bar in the middle, so that one would be off. So that's your 0. So for the next one, we'd say 4B0001. So that's our next value. And then we say display equals 7B. And we want to do all this in binary, at least this part. The sum could be in pretty much any number system, but I find that binary is the easiest to be able to really see what is going on. So for the number 1, that would be 0, 1, 1, 1, 2, 3, 4, 5, 6. And that corresponds to the number 1. Now, I have already copied most of these, as much as I would love to continue typing them, I think you guys should be able to, figure out what the rest of these mean. And this here, this entire thing, this is the decoder that we were talking about in the project. So just to reiterate what a decoder does is you have your sum here. So whatever this smaller outputs, or I guess could really be any size change, but you're taking one output and converting it to something else. So you're saying whenever you get this, turn it in to this. So turn your display into this whenever your sum is 0. And that continues all the way down. Now, we are going to want to put in a default case. So for the default, I decided to just say X's, because you can't really say 0 because that's already a value. It could be, a value of our addition. So I just went ahead and decided to say X. So display equals 7bx. And then we will want to end our case. Let's scoot that back a little bit. Alright, now for one of the trickier parts was the overflow. So here, inside of our always sum block, right here, we would want to say if overflow equals 1, begin. So we want to say that our sum is essentially null if our overflow, or if we have an overflow. So we do the same thing like for the default case here. So we'd say for bx. And we will want to say that our display equals 7, b 0, 0, 1, 1, 1, 0, 1. Now this corresponds to a small o on the 7-segment display. Alright, so then we'll go ahead and end that. And we will end the module. And I want to scoot that stuff up a little bit just to be concise with our coding. Here's where we begin the overflow. Here's where we end it. And here's where we end our decoder, essentially. And decoder. And that is that. So now I'm going to go ahead and whip up a quick test bench for this. So now that we have all of this down, and it seems to make sense so far, I'm going to go ahead, head back up to project. Oops, go to new source. We'll do a Verilog test fixture. Just call it test bench. I have a feeling I probably named one of them, And I want to make sure that our project 2, these match up. Otherwise, we will not get what we want out of our test bench. So next and finish. Alright, so we got our two input registers, A and B. We have our output wires of sum, which is 4 bits. Looks good. We got our 1-bit overflow and our 7-bit display. They're all instantiated here. And we have our initial inputs. So let's go ahead and say, we'll go ahead and monitor our inputs. I'll say, or monitor everything essentially. So we'll say A equals %B, so that means it'll display in binary. B equals %B, sum equals %B, oops, overflow equals %B, and display equals %B. Alright, and then you want to make sure that you are calling the inputs in the same order, or your inputs and outputs. So we go A, B, sum, overflow, and display. Alright, so this will give us a nice text-based representation of all of this. Now, I'm going to go ahead and call everything in binary. They started here with a, decimal representation, but I'm going to go ahead and throw some binary values in there. So we'll go A equals 4 comma B. Let's do a nice one that will yield us a good result. And we'll say B equals comma B. Yeah, so this is 4. So 0, 0, 1, 0, let's say. That's 2. Alright, and then let's go ahead and wait 100 nanoseconds there for our next one. Now, let's go ahead and do one. So 0, 4, 5, 6. So this should result in 6. So we'll do one that results in something over 10. So we are displaying a letter. So here A will equal 4 comma B. Let's say 1, 0, 0, 0. Easy one. 8. And we'll say B equals 4 comma B 0, 0, 1, 1. So that would be 3. Results in 11, or the letter B in the hexadecimal. And then for the final one, we always want to be sure to put that little pause in there, otherwise you'll get one result for your entire test bench. So for this last one, let's go ahead and plug in something that will yield an overflow to make sure that works. So we'll say 4 comma B, let's just do an easy one, 1, 1, 1, 1. So that's 15, or F. Oops, and B equals 4 comma B 0, 0, 0, 1, which is 1. Yeah. Now this will result in overflow, since it's outside of the range of the 4 bits. So let's go ahead and save this and click on simulation up here. Click on our test bench, make sure everything looks good. I don't know why it's doing whole synthesis. It shouldn't be doing that. I just want to... Yeah. I don't know why this thing doesn't like to let me click. Alright, so we'll go ahead and simulate that, and so far we're looking good. Alright, so here we got our simulation window. Wait for that to elaborate. Okay, let's maximize this, check it out. And we'll want to zoom to full view. Alright, that looks pretty good. So, here we've got on our first and on the initialization, we get the correct answer with the correct display. So here we got A, B. Alright everyone, so I just realized that my B and my 6 look the exact same. So let's go ahead and fix that up here. So what I did was I went ahead and added actually let's take that out. Let's add a little hook on 6. So it's full 6, and this is a lowercase b. I hadn't thought that they looked so similar until just now. So let's go ahead and try running that test bench again. Okay, that looks better. So now we can see here that we got all the desired answers that we wanted from our simulation. And this essentially concludes the demo for Project 2. I hope that this has been informative to all of you who got the chance to watch it, and it answered any questions that you had. If you do have any more questions, feel free to email either myself or Alex with your questions. Alright, have a good one.